Swayam Prabha. Digital India. Educated India.
Good morning. So much of this talk will be about what do we know about the universe and how do we know about the universe. Okay. So what do you think? What is your idea of an ideal physicist or how physics is done? I mean, there are two components. So one is that you need to build devices, you need to measure something. The other thing is you need to have a theoretical understanding of whether what you're measuring makes sense. For example, the previous lecture, Lagrangian mechanics, and how all paths are likely but at different probabilities. That's a theoretical understanding which you put forward to explain what you're seeing in a detector in your lab. Okay. So lab is easy, but now for the universe is our lab. So how do we know what we know about the universe? So what do you know about the universe we are in? It's very big. Okay, so let's see. So somebody said very big. Expanding, okay, what else? Flat, okay. What is relativistic?
We have a maximum speed limit as to how fast body can travel.
Okay, that's an observation, but doesn't say anything about how much we know about the universe. Okay, I mean, so that's all covered in expansion. We'll come into all these details. Inherently probabilistic. What does that mean?
As in, like, the universe is quantum in nature.
Okay. Are you quantum?
As in, yeah.
You are.
Those effects are reflected in a microscopic scale.
So it's a question of scales. So in physics, there's always two very important things: length scales and time scales. For example, the theory of you and me walking on this floor is macroscopic. So there your standard Newton's laws apply. Okay. If you go quantum, meaning if you go to point-like particles, the standard technique doesn't explain everything. So for every length scale, there is a new description of there is a new description of nature. This is what we call theory. Okay. So now the question we ask is, often you always go, take a microscope, go smaller and smaller and smaller, and you say, there are atoms, there are nuclei, there are like quarks, electrons, so on and so forth. Okay? What if you expand? Supernova. Okay, let's not go to supernova and all that at the moment right now. But what I want to convey is that, how do you know these facts? Observations. What do you observe? Universe, yeah, but
Redshift. And then by geometry of the universe is kind of that we can then do some calculation on the cosmic microwave background.
so that's all too many details. We'll come to all the details, but first thing is that you should always be able to explain any complicated thing in simple words. Okay. No, I'm asking you, how do you know that? I mean, this is something you have learned or you have read it somewhere.
Yeah, because we see things moving out. We observe that like you said, we observe Doppler shift when
Most of the objects move.
redshifting. When as objects move away from us, the light that comes to us becomes redder and redder. I mean, the wavelength
You're all right in parts and not completely right in other parts. Let's try to clarify that, okay? So, as usual, we are not going to go. Another important thing is, before I start with whatever I want to say, is that, like microphysics, what I mean by microphysics is that what you discover in lab about how electrons behave or how photon behaves or anything applies to electron or photon also in other parts of the universe. They are the same things, the same physical laws go on. So if you understand a theory here on Earth, in principle, it also applies to centers of stars, okay? Sun, white dwarf, whatever. And that is basically, that's what we'll use. As in, given current understanding, we'll observe the sky and we'll figure out like how to observe the sky. I mean, of course, you can, go out in the night and see some stars, whatever and whatnot, but that's not true observation. I mean, there's a technique to it, there's a systematic to it to extract more information from images you see in the sky, okay? So, to begin, so this is roughly what I'll talk about. First, I will survey the local universe with some pictures. You'll understand what I mean by local, because you see the scales are very different. And then I'm going to talk a bit about theoretical understanding of basic theoretical tools and black body radiation, which will be very useful in understanding experimental observations. And finally, I'll come to the holy grail, which is the cosmic microwave background, from which we actually learn all of these facts. But there are other experiments which tell you each of these facts in a slightly different way. But cosmic microwave background is the holy grail that tells you all details that we observe. Of course, that solely relies on our theoretical understanding and how we model whatever we are modeling. I'll come to all these details slowly. So, survey of the universe. So, we are somewhere here, I think, if I'm not wrong, this is Guindy. So, if you go 10 kilometers up in the sky, Chennai will look roughly like this. Maybe some of you have been on a flight and peeked out. So, this is like 10 kilometers. So, 10 kilometers is also what? Edge of the troposphere. Atmosphere is still, as in, that's where most of the commercial airliners fly, 10 kilometers, okay. So let's go farther. The other image is that from the moon. This was taken by Apollo astronauts in 1968 or something, and it's rendered in color, but the key thing is that distance between moon and earth now is at a different scale. It's like 10 to the 5 kilometers. Okay, so we already jumped scales, but physics has not changed. Newton's laws is still Newton's laws. Okay. So then, what are the images of the universe we know of? A curious question I want to ask at this point is that, how do I know this number? When was it first determined, distance between Earth and Moon? So Newton, meaning you are saying only in the 17th century this was figured out. What is the distance between Moon and Earth? But parallax is very difficult. So how do you do all this? If you're using parallax, how do you do it? If you're using eclipses, how do you do it? So the Alexandria story is different. That proved that the Earth is round. Right? It proved that Earth is a circle, based on observing the shadow at noon at Alexandria and shadow of a stick a few kilometers away from Alexandria. So that distance, that angle, basically using S equal to r theta, you could determine Earth is a circle. It has a radius. Okay. But this is different. They're related, but they're different. We always see the moon, but how do you judge the distance? It's not like I can take a scale and measure it, right? So how was it done? Huh? Time periods, okay, let's, well, it's a question of, so Earth-Moon distance. I heard a few answers, let's see. One was parallax. The other one was eclipse. And time periods somehow, okay? So, but which of these methods were first? But it's nice to think about it that way, but doing experiment is hard. Yeah, what if you look from the other eye, then what? How do you measure that angle? So there are a lot of technical difficulties. And who did it as in, many people came to the same conclusion, different civilizations, but only some of them have been officially documented and survived. So who do you think figured this out first officially, like on paper? Galileo. Galileo is too late. They could have figured out, but there are no documents. Babylonia, there are no documents. So it was the Greeks as usual. So Hipparchus was the first guy who figured out the distance between Earth and Moon to be roughly, I mean, of course, there's a factor 2 error or something, but he got the 10 to the 5 correct, which is amazing. This was done in 260 BC. Okay? And all he did was use basic trigonometry. No, not parallax. It was actually the eclipse. Yes. So an eclipse was observed. So moon is here. Anyway, moon casts a shadow. You have a point where you observe a total eclipse, and many kilometers away, it's a partial eclipse. So from this, you know how big the shadow is. So once you know how big the shadow is, again you use S equal to r theta and figure out the distance. You understand the point? So okay, let's work it out. As in, this is the shadow, okay? So this guy devised an experiment, say that they knew when eclipses will come. So he said, okay, let me put one guy here for a total eclipse and another person somewhere who will see it as only a partial eclipse. So partial eclipse meaning you are at the edge of the penumbra, umbra, whatever, right? You are edge of the shadow. So from here, you know this distance on Earth. So it's like a disk. So let's do, so 2D projection is a disk. And you know where the moon is in the sky. So you know the theta. Okay? So, and because the distances are large, you say this is almost a circle. So this is S, this is D. So you have measured S, as in you know S by looking at the shadow, and then you measure theta using a sextant or whatever, you measure the angle. Then using S equal to r theta, you know D. So that's how that was first discovered. And it's amazing that they could get 10 to the 5 correctly in 250 BC. How do you measure it? So you measure it with respect to some vertical reference. And you measure the same thing from two different locations. So you know the delta. That's how you get it. So as you see from this measurement, you're prone to errors in delta S, you're prone to errors in delta theta. So roughly you get that distance. This is how it was originally done. And then to come to this exact number of 3.8 10 to the 5, it took 2000 years. 10 to the 5, people got it in 260 BC. But to get it to 3.8 10 to the 5, you needed time period through Kepler's laws. Okay? And then the precision improved, and now it's very exact. Now basically we have a mirror on the moon, and you shoot a laser from Earth, and you measure how much time the laser pulse takes time to come back. So you know the distance. That's how we do it today. But you see, it's a long journey. This is just the local universe. This is just the moon. But then in the past 50 years, there has been an exponential progress in various things. So what is the next image we have? So this is a pale blue dot, as often Earth is referred to as. And this is seen from behind Saturn by the Cassini aircraft. So this is a much recent image. This is, I think, 2013. But the very first images were taken by Voyager 1 in 1990. Okay. And this, you see, the distance is now billion kilometers. Still, physics has not changed. Everything is as it is. So next, let's go further. So what is beyond solar system? Oort cloud, I mean, okay. Also, what is Oort cloud? Oort cloud is mostly made of icy rocks. Small pieces of ice condensed on rocks. So the Oort cloud is still here. So the next closest thing to the sun is something called Alpha Centauri is here. So that's the distance between the closest star, and that is called what? Have you heard of the word? So distance to closest star up from the sun. This is called a parsec. Okay? And parsec is 3.26 light years. How much is a light year? Distance light travels in a year. So you see, now we had to change units because universe is so big. We have to go from kilometers, billion kilometers, to parsec. So 1 parsec is 10 to the 18 centimeters. So that's 10 to the 15 kilometers. So that's a parsec. So it turns out that the sun is in something called a local bubble. Okay? Local bubble meaning it's an underdense region. The sun is here, let's say. Because we are humans, we are always center of the universe. That's how we like to think. That's why how these images are like that. And then there are a few stars and star clusters around the sun, and all of this is within 100 parsec within the sun. Okay.
How do we get that distance?
So now we can observe the stars. Okay. So you do spectroscopy. So for example, you would have seen about atomic transition lines. So now you take the atomic transition line and give it some velocity. So there you'll observe a Doppler shift. From there you can judge distances.
Saturn isn't a star.
Huh?
Saturn isn't a star.
This is not Saturn.
No. So about Saturn, we have this thing Earth.
So to determine the distance between Earth and Saturn, you mean? For that, Kepler's laws was used. Because you know the time period of Jupiter and Saturn around the sun. From that you extract R. And how do you know? For that you need to know the mass of the sun. So that means You see, you measure, you use the reference as Earth. So it's one is linked to the other. All these calibrations are linked to the other. So it's very complicated experimentally, but that's why it has taken thousands of years to come here. Okay. So these things are done through spectroscopy, and usually farther the object is, your parallax measurement is better. And now we are at a precision where we can do like very precise parallax. We have satellites. Okay. So what is the next step? This is the local bubble, and this is the rendering of the Milky Way. Okay. And we are here. And there are like 100 billion stars in the Milky Way. Okay. And we are here, and most of the stars you see are just, as in with the naked eye, are only from a region, a small region around here. Okay, so a Milky Way is basically 100 kiloparsec. So you're already jumping scales. So size of Milky Way, I think technically it's just 80 kiloparsec. Okay, so it's that big. So you cannot imagine it. I mean, you need to get used to these numbers. That's why these are called astronomical numbers. Okay. And of course, we cannot take a picture of ourselves because so this is a rendering, so to speak. We know our position in the galaxy, and the sun goes around the galaxy just like many other galactic center, like many of the other stars. And that's what we know so far. So far, so good. So what is next after Milky Way? There is precise reasons why it's forming spiral patterns. And this has to do with the fact that matter interacts with light. So have you heard of angular momentum conservation? Okay. So if I take a sphere, put particles on it, give it rotation, but if I make the particles charged, it can emit light. Light carries away angular momentum. So when it carries away angular momentum, it changes its orbit. So they all compress to a disk. And then the spiral is just a small scale feature. But the key point is that you form a disk. Okay, and all this has to do with the fact that angular momentum is carried away by light. So what is next after Milky Way?
So, like you talked about how the distance are how do we know that the Milky Way is 80 kilometers?
Through observations. No. It's far more complicated because you basically look at stars. Let's say we are here and we are looking at this direction and this direction. Okay. So you track many of these stars. You track their positions and velocities and their Doppler shifts. So how far they are moving, how fast they are moving away from us. And from all of this, you can get an estimate of distance. At some point beyond, you'll hardly see any stars from our galaxy. That's when you say, okay, this is roughly the end of Milky Way. Very roughly. But it's not really like that, but very roughly it works like that. This is the radius. We are at 8 kiloparsec from the galactic center. Compared to 80, yes. So this is something like 20 kiloparsec, but 80 is here. Okay. Still, 8 kiloparsec is very far from the galactic center.
So you just said that, like, to determine the size of the Milky Way, you check, you see the stars that are there at the end, and eventually you realize that there are no more stars that belong to the Milky Way, and naturally it stops there. But so how do you know that a star actually belongs to your galaxy or belongs to other galaxies?
That is a different question. So there are errors for it. That brings me to the next part. We are in something called local galaxy cluster. So this consists of like 5-10 galaxies like Milky Way that are going together. And of course, there's a region in between where everything is hazy, but there is a sharp boundary you can set artificially by hand. by looking at their velocity, because the speed you go around is proportional to the mass enclosed. You use that.
So, about the local bubble, so why is its size restricted to 10 parsec?
100. It's not, I mean, this is our definition. 100 parsec because apparently this 100 parsec is a special region where you observe this distribution. Beyond that, there are different clusters, but they come out differently. So that's why I showed you this diagram. What can you understand from this diagram, apart from colors and all of that? So this is basically part of the sky, and this is basically all the galaxies that have been measured. Okay, each dot represents a galaxy. The color indicates the density of galaxies. So it's more dense here. No, hotter is a different question. So this is only a measure of number of galaxy per volume, so density. So there are many close to us, but as you go, there's still networks of galaxies. Okay, and we are here in some galaxy cluster of this sort. Milky Way is somewhere there with other things. And this, the scale of the universe is gigaparsec. So okay, these are all order of magnitude estimates. Precise numbers are difficult to come by at this stage. Okay. So this is basically what we know from optical measurements of just looking at galaxies and so on. Okay. So this is just to give you a flavor of what we know. Next, we want to figure out how we know what we know. Do you understand the point? I mean, you measure these things. I said, there is this star, it's moving this way, spectroscopy. I use many of these words. But the starting point is basically black body radiation. You just finished your 11th grade, right? So you would have easily encountered black body radiation. What is it? Emitted by a black body. Okay, great. I think that is all correct, but that's not the essence. So what is the essence of a black body? Oh, you're just giving textbook definitions. I don't want that.
For all the for any number of photons that it absorbs, it emits them in like some pattern, like it's like
Yeah, that.
In all ways.
Radiates all frequencies of light.
So that is the correct definition. Temperature. The black body is a good absorber and a good emitter. Fine, but how it emits is solely dependent on the temperature of the body. Okay, and that is the defining characteristic of a black body, that it just depends on temperature. So a black body spectrum, we call it B nu, basically goes like this. Have you seen this before or not? You have not seen this before, okay. You would have seen this in some form. No? Okay. Anyway, so you're learning something. E is the exponent. Like ln, L to the base E, that E. Okay? Exactly, yeah. So if you haven't seen it, this is the most important thing you will need in cosmology and astrophysics to start out with. Okay, and you see it depends on the temperature this way, and nu is the frequency. So what this means is that if I fix the temperature, and I plot this function as a plot this B as a function of frequency, you see this gray curve here? That's the sort of curve you're supposed to get. B is the intensity, spectral irradiance. It's energy received per meter square per wavelength of emission. Okay. So watt per meter square? Joule seconds. No, like a watt, a unit. Okay. So it's energy received as a number of photons received per centimeter square of certain energy. So this is a very interesting thing. Sun is actually a very nice black body. Who would have thought? Okay. So you see that this gray is a black body spectrum, meaning I take this function. C is speed of light, h is Planck's constant, k is Boltzmann constant. I fix temperature to be 6000 Kelvin. This is the surface temperature of the sun. If I do that, I get this gray curve. Okay. And then you measure it, okay? Then you send a satellite up, or you can do it even from the ground. You measure the spectrum of the sun without theory. I mean, you just take a camera, a very nice camera, that can measure all these wavelengths. And that's the yellow curve. That's your experimental determination. Then you put one on top of the other. And you see there is a very big overlap. Of course, there is a small error. This depends on, because it's not stationary, there is convection inside the sun, so there's plasma and all that, so there are small errors. But roughly, it is a black body. Okay, and all of this is determined by the temperature. So where is the peak? No. I'm asking wavelength. So what is this called? Optical range. Yeah, visible wavelengths. What is the, how big is your iris? I mean, the black part where the light enters inside your eye. With intensity, night or day or whatever. Let's say on average on a day like this. It's a few millimeters. You know why? No. It has to do with this. Because we are on Earth and we are evolving on Earth. So the size of the eye has evolved to see best in optical wavelengths. Okay, so the size of the eye is related to the peak of the spectrum. I think this is an evolutionary trait. No, those are corrections. Meaning, these are higher sophisticated developments of the brain that makes you a better predator. I mean, you can focus on some point and all of that. I'm saying very naively, as a first approximation, the average eye, the size of the average eye is related to the wavelength, because you can only see that light that can enter through the lens. If the wavelength is larger than the lens, you won't see it. For example, here, this is called infrared. You can't see infrared light, right? I mean, nobody says you can see infrared light because the wavelength is larger than our eye. So the wave doesn't enter. Or only a part of the wave enters. But biologically, our mind is not. Biologically, we are not optimized that way to see that. So biologically, we are optimized to see this. So this is one of curious things that came about just by looking at this. This is 1901, Planck. He figured this out. And soon after, people figured out it must be due to this. Okay, so which is quite amazing. So So this is one thing you have to keep in mind. Temperature is related, so black body is related to temperature, and everything, the spectrum is purely determined by that function. Okay. So next. So the break is at 11, right? Okay. Let's see how far I can go. So other things. So some people said very big expansion flat. Before going into CMB, how do we know universe is expanding? So what is redshift?
Redshift is the wavelength of light shifting.
But why should it shift?
Because it's like if light is going over the space and the space itself is expanding, then light will also, the wavelength of light also.
So
So if things are farther away, then they'll appear more red than.
no, these are words you have learned, but what is the theory? Well, you agree, disagree, it's all fine, but I'm asking you, what is the theory? What is the basic idea?
Light travels.
I might be wrong, but the basic idea I think is that light can actually shift when it passes through millions of clouds, and it lets only the normal wavelength.
That is called attenuation. That has nothing to do with what I'm trying to say. Okay, let's do some, before the break, let's try to give this some more, a better mathematical footing. So you guys know Pythagoras theorem, right? What does it say? So Pythagoras theorem says, so if I'm in 3 dimensions, so distance between 2 points, the shortest distance between 2 points is a straight line given by this expression. So the key point of light is that light is relativistic. What does relativistic mean here? Travels at speed of light for light. Okay, it's very precise. So this is no longer a good measure. For me and you, or whoever, delta S, how much did you travel today, is a good measure. We can use this to do whatever. But for light, for relativistic particles, there's another parameter, another coordinate, which is the time coordinate. So for relativistic particles, distance traveled in space-time, not just space, what matters is space-time distance, is given by generalization of this. Okay. So there's a minus sign. So this is the time part, this is the space part. I mean, how do you judge this? How do you make use of this? For example, I turn on a laser now. So I know T0. You go to other side of Chennai and you measure that light. So that is T1. So there is a delta T, and you know delta X, delta Y, delta Z. So you know how much light has moved in space-time. Okay, so this is what matters for cosmology. This is what matters for light. This is relativistic. This is also known as the metric for people who haven't encountered this word. But basically, this distance between space-time. Okay, you had a question.
Isn't C delta T just the distance that light has traveled?
Exactly.
And then you're subtracting it again by the distance.
No, but these are distance light has traveled is C delta T. But delta X, delta Y, delta Z are your positions where you are measuring things.
Distance that light has traveled is not directly given by the distance, by the distance between the positions.
It's a very good observation you guys are making. For light, this is actually 0.
Yeah, exactly. Yeah.
That is true. This is called a null geodesic in general relativistic terms. But this is where the redshift comes in. This is where fundamentally a redshift comes about. Okay. So far you cannot say anything about redshift here. What you have to do is that, because somebody called Hubble, he drew a straight line through a scatter plot. It became Hubble's law. He observed that as you move farther away, objects move at a faster speed. Okay, so this was the conclusive evidence for expansion of the local universe. Okay. So that means that my coordinate system, if something is expanding, my coordinate system is changing. Right? So what does that mean? So let's say I can draw a coordinate system 0, 0, something like this, at t equal to t0. It becomes bigger, let's say. But then I'm using something called co-moving coordinates. So physical distance is some function a of t, or whatever, t1. This is, let's say, this is at t1. Okay. So here a is whatever. You set up your coordinate system that x is rescaled by a factor a, y is rescaled by a factor a, z is rescaled by a factor a. So that means your new line element, delta s square, will have some new factor, a square of t okay. This is called a scale factor. So this is a function that depends on time, okay, by convention. So if you are expanding your coordinates in a controlled manner, I can absorb that expansion in x, y, and z. So your line element will look like this. Okay. So for light, in an expanding universe, this is still 0. Okay. So that means so using that, you can write, I can say ds is 0, or ds square or delta s square is 0. So this means lambda observed over, lambda is the wavelength here, so E means emitted, O is observed. So time at which something is emitted and time at which something is observed. Z is the redshift. Okay. So what redshift indicates is that how much is this scaling has changed. So how much has your coordinate system expanded in physical coordinates? No, velocity C is fixed. So exactly.
Because the space itself is becoming bigger.
So I have a given wavelength, but then I'm stretching the coordinates. So wavelength will also get spread out. Okay. So this is expansion. For contraction, I squeeze the coordinates. It will be bluer. So everything will get shifted. So what is all this red and blue?
Higher frequency, higher frequency, lower frequency.
What?
Like, because we say that blue is for us in the visual spectrum. Blue is at the lower wavelength, red at the higher wavelength. So it's like how
So yeah, I mean, you would know this Vibgor, the rainbow thing, right? So below violet is ultraviolet, above red is infrared. It's as simple as that. The point is, if your coordinate system is expanding, and if it's expanding, that means what? This is larger than this. So wavelength observed is larger than wavelength emitted. Okay, this is what redshift means. All those things you said earlier in words is absolutely right, but it comes from a very basic principle of this sort. Okay, and this is different from a Doppler shift.
So that was my question. Can't you explain this through a Doppler shift? By saying that since there, like, if say there is a star that is emitting light and it's moving away from us.
At some velocity,
Yes.
sure.
Then won't any light it emitted be redshifted?
No, that imagine star is moving away from you at some velocity, but also your coordinate is changing. Light moves at the same speed, but the object. So for what is Doppler? What is the formula for Doppler? Do you remember? I mean, Doppler shifted frequency. Formula doesn't matter. Okay. The point is, I have a star moving at velocity v. This has units of meter per second. Now if my coordinate is stretching, this m meter will be rescaled by this factor a. Okay, that is redshift. What Doppler does is that I have v and v observer, and saying the change in frequency is related to change in difference of relative speeds. But this is really rescaling of coordinates. This is observable relative motion. This is rescaling of the whole coordinate system.
But then why is this the conclusion we came to and not Doppler?
I mean, no. So that is for the light, okay. This is for the star. So let's work this out. At t emitted, a star is moving at velocity v, but then light moves at velocity c. At t observed, there is some expansion. This is still moving at some velocity v prime. Because of expansion, the wavelength of this light has changed. But this thing is still moving. The change in this wavelength is independent of this motion. Right? That's what this equation tells. So they are different things.
Sir, I get that there are different things, but like, why do we choose one conclusion over another?
We're not choosing any conclusion, right? I mean, these are
Sir, no,
facts.
I think what he asking is, if you were to just notice some, some change in frequency of light from what we expected to be at the source, then why would you assume it's automatically redshift and not Doppler?
Because Doppler shift depends on relative velocity.
Yeah, and it doesn't match relative velocity.
Exactly. Doppler shift is a correction on top of this. So there are two different contributions. Both are there. It's not that we are choosing one over the other. Both are there. The Doppler provides a small correction to all of these things.
Swayam Prabha. Digital India. Educated India.